Got it.
Okay. Thank you.
Steven and Tim, look who's doing this for you.
Oh yeah. Thank you, Andrew.
Close up. Scary. Are we on?
Yeah.
Like, can you see the board?
Yeah.
Okay, so now the next kind of problem that we should at least be exposed to before you try to do this and you get very frustrated on your own. Here are, and there's a couple questions just like this in the book. Here are some things that could either oxidize or reduce, possibly. If these are all reducing, another expression for that is they would be oxidizing agents. Remember talking about agents before? It's confusing because the thing that reduces in a reaction is the oxidizing agent. Yeah. And the thing that oxidizes is a reducing agent. Okay, but anyway, we're talking about oxidizing agents, so things that are reducing. Would you use the table, the reduction potential table, determine which one of these is the worst at reducing, and rank them from, I think on the answer key I have, from the best to the worst. So find which one reduces the best, and rank it down to which one reduces the worst.
Somebody give them the notes.
Oh,
Yeah,
covered
I
up.
just covered it.
Yeah. So try that. Take a moment and see if you can look those up. Come up with, there's no other way to do it. And you'll always get the reduction potential table. You don't memorize terms on there, or reduction potentials or oxidation. Just use the table. I guess I never gave the answer to the previous slide problem. It was negative 78 kilojoules. Did you come up with that? Negative 78? 79, yeah, that's fine. All right, the reduction potential is up here. Reduction of cadmium is negative 0.4 volts. Reduction of iodate is positive 1.2. Potassium, not so good, negative 2.92. Potassium is not interested at all in reducing to metallic potassium. Better at oxidizing metallic potassium to this, to that. Now water is kind of an oddball, isn't it? Did you struggle with the water? We're looking for the reduction of water. Now water, the hydrogen is positive 1. That part of it can reduce. O is a negative 2. O can't reduce any more than negative 2. So it's the hydrogen. So when water is reducing, you'd produce hydrogen gas. So look for water to make hydrogen gas. And it's going to be about the middle of the left side. No, it's not.
It was on the right.
It's on the right side. I was thinking oxidation. It's on the right side, just past halfway down. We have water making H2. It also makes us hydroxide ions because it's only the first hydrogen in the term that one of them that leaves. but the reduction of water is not favorable. It's 0.83, negative 0.83 volts. And then that gold chloride complex, about, I don't know, 2/3 or so of the way down on the front, the first column, 0.99. So, if we want to know the ranking of each of these, it's going to look like this. The most positive reduction potential is the IO3, so that is the best oxidizing agent, or the best thing at reducing. The worst thing at reducing would be the potassium ion. It's not interested, doesn't want to go there. Did you come up with that ranking? Those 5 in order? Anybody have any questions about any of them? Water can oxidize and reduce. If it reduces, it makes hydrogen gas because the positive one can go to 0. If it oxidizes, the oxygen becomes oxygen gas because it goes from -2 up to 0. So water could both oxidize and reduce. And the next slide, this one is going to be a little bit more challenging because this time we're going to look at the oxidation of these things. So take each of these. Now, this table is a reduction potential table. So if you're looking to oxidize something, you need to find it in the products of an oxidation and turn the reaction around. And then you'll change the sign on the reduction potential to make it an oxidation potential. So try again, now looking for these things in the products and turning the equations around. I'll give you a moment. Find a ball. It's a little bit challenging, isn't it? Just getting the feel for what it means to oxidize and using a reduction potential table to find information about things that are oxidizing. Here is the ordering. The hydride ion, we're looking to cause the oxidation number to go up by gaining electrons. Not by gaining, by losing electrons. H negative goes to H2 very, very well. So that's going to be our best thing at oxidizing. And the worst thing is the fluoride ion. It does not have any interest in becoming F2 gas. It's way more stable when it has a chance to gain an electron and have that extra electron to complete its valence shell. So that means this thing is very stable. It doesn't tend to oxidize. Yeah?
What defines the strength of oxidizing or reducing it? How are you going to weight the potential to multiple singles?
Yeah, when we're looking at something oxidizing, you have to find it in the products. Now, the only thing that would be an oddball, I think there's only one equation that has each of these in the product, except maybe for water. Water does show up quite a bit. But you're looking for water. Now, remember, this is oxidation, so you have to find water in the products, and it has to oxidize into O2. So you have to find O2 on the reactant side and then turn it around. And that would be on the left side, about halfway down. See the reduction of O2 to make water? Well, it's the 1.23. Find the 1.23 voltage.
Oh, yeah.
See it? The rest of them, I think, there's only one half reaction that has the rest of these in the products, and so you just use that. Yeah, yeah. Just know that when water is reducing, you get hydrogen gas. When water is oxidizing, you get oxygen gas. Okay. I have one thing left to show you today. It's got 2 slides, and we really should be getting through it today so that we can see a couple of examples tomorrow and then move along. Now, remember I talked about standard conditions, how that table in your book, and it says the title of the table is Standard Reduction Potential. That means that all solutions are at 1 molarity. Even the products, you must start with products that are at 1 molarity if you want to use that table. And as soon as the reaction starts to proceed, as soon as it starts to go to the right, these will go down and those will go up. And so it only takes a moment in time to not be at standard conditions. Because as soon as the concentrations start to change, then you're not in standard conditions anymore. So we should be able to determine what voltage a reaction has if it's not at standard conditions, because it's way more likely that it's not at standard conditions than if it is. Okay, so if we are standard, that means that all solutions are going to have a concentration of 1 molarity. Now, I didn't have anything under the iron because it's a solid. And all you need is some solid there. You don't have to have a concentration of a solid. But for all the aqueous things, we do. So we could use the table to figure out what the standard cell potential for that reaction is. If we did, we would find that the cell potential is positive. Positive cell potential means what about the reaction? That it's spontaneous. That's right, a spontaneous reaction. Yep. So that means it's going to go to the right spontaneously. What if we started with not 1 molarity, but 2 molarity of MnO4, the reactant? What would that do to the reaction? Would the reaction still occur? We're taking an already spontaneous reaction and we're making it reactant heavy. We're adding more reactant to it. What's that? It is going to cause the shift toward the products. And I appreciate you using the word shift because really you could think of it, it's not an equilibrium reaction, but it's kind of like Le Chatelier's principle. It's going to go harder toward the right side. So the transfer of electrons is going to be more profound and more forceful, and it is Le Chatelier's principle. It says, Le Chatelier says that the reaction will favor the forward direction and even push electrons more from the end of the cathode if you're reactant heavy, if it's reactant heavy. So you'll have a higher cell potential as the concentration of reactants increases. Okay, now what about this? Let's take this back down to 0, not to 0, to 1, and increase the product concentration. If this is 1 then, but these are 2 molar. Will it still be spontaneous in the forward direction? I'm going to contend that yes.